In this video, we'll be talking about error propagation. This is part 2 of our series on error propagation. If you missed part 1 of the series, be sure to go back and watch that one first. I will link it down below in the description, as we'll be using concepts discussed in that video to solve the problems in this part 2. Let's start with this problem. You have a 50 milliliter burette that has an accuracy of plus or minus 0.2 milliliters. Part A asks, what is the percent error to dispense 50 milliliters? In the last video on this topic, we found that the percent error formula is equal to error, or the absolute error, divided by our measured value, and it's this quantity, times 100. And we deduced that this error divided by value term is actually the relative error, and we discussed that in length in the last video. We can just get rid of that real quick. Okay, so the percent error to dispense 50 milliliters. So we know that our absolute error, which is this term right here, is 0.2 milliliters, as this is the error in the burette in one measurement. This is the uncertainty that is present in each measurement. So this is our absolute error, and is in the numerator of our relative error term in the percent error formula. Okay, so let's simplify this formula down now. So I have a percent error is equal to the absolute error of 0.2, or 0.2 milliliters, divided by the measured value that we are seeking, which is right here in the beginning of the problem, 50 milliliters. And now it's this whole quantity times 100. Okay, and now if we put this into a calculator, it'll come out as 0.4%. And this is the percent error of the burette in dispensing 50 milliliters of fluid. So it's quite a low percent error. So this tells us that we have high confidence in the burette's measurement for our 50 milliliter step. Okay, so now let's go into part B, and let's test the same knowledge with a slightly different desired value. So this time it's asking for the percent error to dispense 100 milliliters of fluid. Okay, so let's start by writing a percent error formula once again. Actually, I don't think we need to write it once again. It's right up here if you need to reference it, but we'll just start writing in the numbers. Okay, so this time we know we have 100 milliliters. Okay, so just start writing our percent error. We know we want 100 milliliters. So this time we actually need to take 2 measurements, because we know we have a 50 milliliter burette. So at most it can hold 50 milliliters. So to take the least amount of measurements, that means we have to take 2 measurements, or use the burette 2 times. So I'll actually clear out this percent error here. And what we need to do now is, since we're taking 2 measurements, we have to find the absolute error, or the error that will come out from taking 2 measurements. And to do that, if you watched the last video, you know that we have to use the root mean square method, or the RMS method, for error propagation. So that states that our final error is equal to the square root of the sum of all the initial errors, and that term is squared. Okay, and we know that we take 2 measurements, and each measurement has an uncertainty, or an error, of 0.2 milliliters, as we saw in the beginning of the problem. So we will sum up those errors, and we will do 0.2. This is just our sigma notation again, so we're going to sum up these 0.2 milliliter errors, and we take 2 of them because we need 100 milliliters of total fluid. Okay, so 0.2 squared, we'll just extend our square root here, and we're going to add another 0.2 squared. And this is going to come out to plus or minus 0.28 milliliters. That was a really bad M. 0.28 milliliters. And this isn't our answer, but this is our absolute error, okay? Or the numerator that is in our percent error formula. That comes out from taking 2 measurements using the burette. And an interesting note is that it goes up compared to the original absolute error up here of 0.2. The 0.28 is actually higher. And when you see that by taking more measurements, our absolute error will end up increasing. So now we'll apply our percent error formula. We know that the absolute error now is 0.28 milliliters, like we just calculated. And we're going to divide that by a desired value, which is the 100 milliliters right here. Okay, and then you're going to multiply this absolute, or this is the relative error. Remember, this is relative error. We'll multiply that quantity times 100 to get our percent. And this right here is going to work out to 0.28%. It's the percent error for taking 2 measurements using the burette and getting a total value for a fluid of 100 milliliters. Part C of the problem states, is the absolute error higher or lower for dispensing 100 milliliters versus 50 milliliters? Explain why. So the absolute error for part A, which was the 50 milliliter part, for one measurement using the 50 milliliter burette, the absolute error for that part was equal to 0.2 milliliters, as was stated in the problem, and that was for one measurement. So for part A, we saw that the absolute error was equal to 0.2 milliliters. We can even write plus or minus, write that a little bit better. Plus or minus 0.2 milliliters. And this is for part A. And for part B, using 2 measurements in the 100 milliliter method, or step, we saw that using the root mean square method for error propagation, that the absolute error after 2 measurements came out to be 0.28 milliliters. Okay, so as you can clearly see, the absolute error increased. Okay, so 0.28 milliliters is greater than 0.2 milliliters. And that means the absolute error, the error for the 100 milliliter measurement is greater than the error for the 50, that looks like an 80, the 50 milliliter measurement. And that means we can circle higher. And the reason for this is that as we take more measurements, the errors will aggregate. And that means that they will compound on each other. And so as you take more measurements, there's a greater chance that you'll have more error. And the absolute error then will have to increase. And you can easily see this in the root mean square formula that I'll write up here. As we've written a few times now in the past couple of videos. Basically, this absolute error, this EF, will have to increase if you continue to increase this side of the equation because they're directly proportional. So as you increase the number of measurements you're taking, which is right here, the absolute error on the left side of the equation will have to go up, okay? So if you're taking 2 measurements in this case, the 100 milliliter method is definitely going to be higher in absolute error than the 50 milliliter method, which was simply 1 measurement. Okay, so now let's go into part D. Is the percent error higher or lower for dispensing 100 milliliters versus 50 milliliters? Explain why. Okay, so let's think about the percent error for this problem. In part A, the percent error was 0.4%, and that was for the 50 milliliter. And in part B, the percent error was 0.28%, and that was for the 100 milliliter. So it's pretty clear to see that the percent error for the, I'll just write this out here actually, we'll do 0.28% is less than 0.4%. and the 0.28% was the 100 milliliter, and the 0.4 was the 50 milliliter. So it's clear to see that the 100 milliliter percent error is actually less than the 50 milliliter percent error. And this is really the case because as you take more and more measurements, your confidence in those measurements is increasing. So although the absolute error is increasing, the percent error will decrease because you're becoming more confident in the measurement you're taking as you take more and more measurements. And you can also look at this as the randomness of the errors. We talked about in the last video how the errors offset each other. And this actually ties to the percent error because the percent error will continue to go down as you increase the number of measurements you take. And in the end, this means the percent error will be less as you take more and more measurements because random errors will offset each other. That means you'll have a lower percent error for more measurements taken, as in the case of the 100 milliliter method in part B of this problem, when the burette was used twice to gather 100 milliliters of fluid. So the correct answer for part D then is that the percent error is lower for the 100 milliliter method using the burette. Just one more quick note on part D of that last problem. We talked about how as we increase the number of measurements n, the relative error went down. And this is because as you took more measurements, some of those errors, all those errors are random. And so some of them will offset each other, and in the end, your relative error will decrease as you increase the number of measurements n. So I want to just tie this into a mathematical or quantitative analysis of why the percent error actually decreases as we take more and more measurements. And so we can also just write that percent error also goes down here. And we can look at the percent error formula to easily see this. Sorry about that. Forget percent. What is happening? Percent error. And we know this is equal to the error over the value times 100. And this quantity here is actually the relative error, which is right there. And we see that as n increases, the relative error decreases. And so if this entire quantity here, where our relative error term is going down, that means this side of the fraction is going down, and it's directly proportional to the percent error side of the fraction. So that means the percent error will be decreasing as the number of measurements n increases, and as the relative error, or the error over the value, decreases. And that wraps this video up on our second part and our second problem of error propagation. Thank you so much for watching. If you have any questions, be sure to leave them down below. I hope this video was helpful in your understanding of this topic. Thanks again for watching, and I hope you have a great day.